Hey, what's up guys? We're going to look at metallic bonding this video, and here we're definitely going to start looking at the more A-level side of this stuff. Before we start, please like, subscribe, share. The subscribers are growing. I want that to continue to get to as many people as possible. Let's get into it. So metallic bonding, first of all, is, again, a bit like ionic bonding. We've got the electrostatic attraction between positive metal ions and delocalized electrons. And with this as well, our structure at room temperature is always going to be a giant structure, all right, apart from mercury. So we've got a giant structure. So we get this kind of thing, right? So if we take this, if we say that this is something like lithium, if we look at lithium here, lithium is in group 1, so it has 1 electron in the outer shell. Right, so if we quickly draw the electron structure of lithium, we have something that looks like this. Right, so again, all of this full outer shell stuff, this electron becomes delocalized and starts moving around the giant structure. So this is what we've got here. So here we've got our Li plus ions, and here we've got our delocalized electrons. Now this means a few things. One, we've got pretty strong bonds here. So we've got high melting and boiling points. Again, giant structure, lots of energy required to overcome the forces. We've also now got these charges that can move throughout the system, can move throughout the structure. So because we've got delocalized electrons, we've got those two things that we need in order for something to conduct electricity. We need a charge or charged particles, and we need that charge to be able to flow, to move. And within a solid, delocalized electrons allow that to happen. Okay. If we go down to the bottom, here we've got something like magnesium, right? So here, magnesium is in group 2. And so this is going to have 2 electrons in the outer shell. So again, if we quickly draw the simple electron structure of magnesium, it's going to look something like this. Sorry, it's a bit wonky, but it's going to look something like this, right? 2, 8, 2. And it's these 2 outermost electrons that become delocalized, okay? So what we're left with, this time, the Mg is an Mg2 plus ion because it's lost 2 electrons, and we've got these electrons flowing through it. And you'll notice a few things, right? You'll notice now we haven't got these 1 electron per ion free. Now we've got 2 electrons per ion free. So this is going to be interesting in that magnesium is going to be a better conductor of electricity than lithium because we've got more of these charged particles that are able to move through the structure. And again with metals, the interesting thing is that because of these delocalized electrons, these can now sort of slide, right? So these are malleable, these can bend, and it's because of the electrons that allow these ions to sort of slide past each other, okay? Now that's where we come to alloys. So an alloy is a mixture. So we've got alloy, mixture of metal plus small amounts of something else. So for example, like steels are going to be predominantly iron with like 5% carbon or something like that. And what that means is now that neat structure has been broken up by this bigger atom. So now the sort of sliding that we get here is not going to happen because that neat structure doesn't exist. All of a sudden, as these slide, they're going to be bumping into that larger or smaller atom. It doesn't really matter. It's just the fact that the neat layers are now interrupted, and so we don't get that. So that's basically like the GCSE side of it. Now we can get into more of the A-level stuff. And where we get to the A-level stuff, we start thinking about something called charge density. And what I think that's quite similar to is it's quite similar to the strength of like an orange squash drink, right? So if we put in a little bit of orange squash and then we fill up the rest with water, we're going to have quite a weak drink, right? Whereas if we add quite a lot of orange squash and again we fill up the water to the same amount, this time we're going to get a much stronger drink, right? And that's about the density almost of this orange squash concentrate, okay? So I like to think about it in those terms a little bit. So here, if we have something with a 1+ charge, and here we've got something else with a 1+ charge, which of these do you think is going to be able to form stronger bonds? Hopefully you can see it's going to be this. Because we've got a much smaller area where that +1 charge is concentrated, it can be felt more strongly. So now the attraction felt between the positive metal ion and the delocalized electrons is going to be felt much more strongly. Whereas this +1 charge here, because it's over a bigger ion, it's going to be felt less strongly because that +1 charge is spread across the whole atom, okay? The whole ion, sorry. And we get this sort of pattern in the periodic table, right? So clearly, as we move down the periodic table here, the atoms are going to get bigger. We know that they're going to get extra shells of electrons, so they're clearly going to become bigger and bigger atoms. Also, as we move across the periods, we start to get smaller atoms, right? And again, we can draw a quick diagram to show that. So if we quickly draw the electron structure of lithium, we've got 3 protons in there and our 3 electrons, okay? Then if we go to beryllium, this time we've got 4 protons with very little difference in sort of the electron shielding here. And we'll talk about electron shielding a bit more later on. But what that means is that the electron shell, the outermost shell, is drawn in a little bit closer. So as we move across the period, the size of the atom or the ion gets slightly smaller, okay? So here, charge density. For a high charge density, we need one thing we need is a smaller volume. Or in this case, we're going to talk about atomic or ionic radius. And in terms of our atomic and ionic radius, the things we need to think about are how low are we in the periodic table and how far across are we in the periodic table. The further across, the smaller. The further down, the bigger. Okay. The other thing we're going to think about in terms of charge density is the charge. So if we take lithium and beryllium, there's going to be 2 good reasons why beryllium is going to have a higher melting point than lithium, right? So lithium is going to have a 1+ charge. Beryllium is going to have a 2+ charge. So the charge density of beryllium is going to be much, much higher because we've got a slightly smaller volume and we've got double the charge. So for both of those reasons, the attraction between the delocalized electrons and the positive metal ions are going to be much stronger, therefore more energy required to overcome the forces. Let's look at a few more examples. So, first of all, lithium and beryllium, exactly as I just said, which has the highest melting point? There, that's going to be beryllium, because we've got Be, it's a 2+ charge, Li only 1+, and Be smaller ion. And our sort of general explanation is, therefore, stronger attraction between positive ion and delocalized electrons, therefore more energy required to overcome forces. So this final bit is almost going to be your it sort of captures everything, right? So we're not going to write this every time, but this is going to be your blanket answer at the end, is stronger attraction between positive ion and delocalized electron, therefore more energy required to overcome the forces. So again, we're not going to write that every time, but in a GCSE, in an A-level question, we would. Nice. On to the next one. So here, lithium and sodium. So if we look at lithium and sodium, we can see they're both in group 1, so they're both going to have that 1+ charge, but sodium is lower down, so it's going to have a bigger atomic radius. Okay, therefore lithium is going to have the higher melting points. So we'll circle lithium, and here both have 1+ charge. But Li atomic radius is smaller. And again, therefore, stronger attraction between positive ion and delocalized electrons, therefore more energy required to overcome the forces. Next, sodium and magnesium. So if we look at the periodic table again, hopefully we can see sodium a 1+ charge, magnesium 2+, slightly smaller atom. So it's clearly magnesium. Magnesium, Mg2+, versus Na1+, Mg also a smaller ion, and again that sort of catch all. Therefore, stronger attraction between positive ion, delocalized electron, therefore more energy required to overcome the forces. Next, lithium and magnesium. So here, lithium, 1+ charge, magnesium, 2+ charge. Now, lithium is going to be a smaller atom, so we sort of need to think about which of these is going to have a bigger effect, right? And hopefully you can probably guess the 2+ is going to make a much bigger difference than the slight difference in size of atom, right? So here we're going to say magnesium, Mg 2+ versus La 1+, despite Mg being a bigger ion. Difference in charge. Means stronger attraction between positive ion, the localized electron, therefore more energy required to overcome the forces. So that's your discharge density idea. I think we're not going to generally talk about charge density within our answers, but we're going to use this idea of charge density and what it means in terms of our smaller atomic and ionic radius and our charge. We're going to talk about these two things every time we answer something that's comparing our two metals. Okay, now let's get back to this. Is the question we're going to basically finish this question, right? We're going to finish the question that we looked at last time. I am going to tell you the answer for in respect to bromine now. So if we look back here, bromine. Now, here we've got a pretty low melting and boiling point in terms of kelvins. Remember, we'd have to plus or minus 273 to think about that in degrees. That's negative numbers, right? So because we know it's going to be a liquid at room temperature, we know it's basically going to be a simple structure. So we'll say bromine, we should know it's Br2, simple structure, or molecule. Weak forces between the molecules, and therefore low energy to overcome the forces. And this is the important bit, right? Weak forces. We'll look later on at what those forces are, but we'd be talking about van der Waals forces there, or van der Waals, and we'd need to make sure we're talking about between the molecules. All right, great. Hope that's helpful. See you next time, where we'll be looking at some more structure and bonding stuff, more of the A-level stuff. Until then, happy revising, guys.